what a process group is, what your parent process is, what your group leader is, what your session is, and what your session leader is. We'll then walk through syslog, so you don't always have access to standard in, standard out. How do you write data that you want to see what your process is up to? I'll do some signal handling, so how do processes receive signals? How does that control the process? How does shell job control work? And then we'll go to examples of writing an actual daemon process. So a daemon or a daemon, depending on how you want to pronounce that, D-A-E-M-O-N word, is something that will run beyond any session you have with the computer itself. So we'll talk about what a controlling terminal is, where to find these things in the manual that's included with Linux, and then how to do this both the hard way, which I worked for a company initially 20 years ago, left about just almost 10 years ago, where we did a lot of low-level programming, we did a lot of systems programming, we had communication agents for SATCOM for the Army, and all these things would talk to hardware and run at a very low-level abstraction, so we were writing agents and daemons and all sorts of things. So we can get into some of that, and then I'll show you how to do it all with systemd, which is so ridiculously simple, you should really never do it the hard way ever again. And you get a lot of capabilities for free. So with that, we're going to start. So the first thing I'm going to do, all of these labs we're going to go through today, and there's plenty of time to get through this material. It's only 10:30, so I doubt we'll go to noon. Git clone, let's see, github.com, and I can send these links to Mark or post them to the meetup site.
Yeah.
So I have a KeyLUG repository where I keep all of the code for any sessions I'm going to do, starting with this one. So we can just go ahead and clone this. And if we drill into here, there's a processes and daemons subdirectory, and there's a bunch of labs we're going to walk through. So the first one is going to talk about processes, process groups, and sessions. So before we do that, let's talk about the manual system in Unix. So anything you want to find about the Linux programming environment, the APIs that are available, the functions that are available, you can look up. And the interesting thing about processes is they're in a very intuitive location called credentials in section 7 of the manual. So if you ever wonder where to read about processes, groups, and sessions, that's what you want to search for, is man 7 credentials. So if we hit this, you're going to see some good definitions here about a process, a parent process, and several other topics. So one thing to keep in mind, the Linux kernel has one process table. Everything that runs on the kernel is an entry in the single process table. There's not a bunch of them. There's not different process tables. Containers use something called namespaces in the kernel to alias this, but your Docker PS, your Kubernetes pod, whatever you're running, it's going to translate to an actual process ID running on the kernel that's hosting your system. So there is only one process ID or one process ID table. Some processes are special. So what is the most special process on your system?
PID1.
PID1. So what's it do?
Kernel, right? Or no?
It's not technically the kernel. It's the first process running in the system. So PID0 is its parent, and PID0 is the parent of a few things. But you'll notice that PID2 is actually a lot of your kernel threads that are running. So process ID 1 is the ultimate parent for any processes that are orphaned. So it will reap processes, and what it does is it waits on those processes to stop. And that has to do with signal handling. So all processes cannot live apart from a parent. So if your parent exits after he's created you, you will get reaped by process 1. You won't be left alone in the cold. So, but the first process, it used to be the initd daemon that would handle starting everything up in order. Systemd is kind of the newer version of that. One of the things systemd brings to the table, initd was based on a lot of scripts, so it was very easy to see what was happening when, but it was very serialized in nature. So each thing would kind of start up in order, even though some of that serialization was artificial. Systemd decided to parallelize a lot of this. Some of the, I guess, discussion around systemd, there was sort of controversy there. It used a lot of embedded code or C code to do these things rather than shell scripts, so it was less intuitive than what had come before it. But it's extremely powerful, and Linux systems can now boot up in seconds. So systemd will analyze all the dependencies of things and what needs to start in what order, and then parallelize that as much as possible. So, and then it'll manage your daemons themselves. So you can, with I'll show you the last example here. You can create a systemd service file, and then that will start your process. If your process dies, it'll restart your process. It'll give you some defaults for your process, so you don't have to go program a lot of stuff if you want to run as a daemon. This, you can write a simple Python web server or anything and have it just pop up as a daemon and run just by a simple unit file in systemd. So, and then have all these auto restart capabilities and things without having to code anything. So it's very powerful. Let's walk through this though. We're just going to start with the basics here. So I talked about a process ID. Every process has a parent. You can always get your PID programmatically by calling get PID. What does this number 2 mean next to this function? Sometimes you'll see a 3. What does 2 indicate? Okay, so anything in manual section 2, you're talking to the kernel. This is the system call interfaces. Manual section 3, you're talking through the libc standard library that's likely under the hood going to be talking to the terminal. A lot of the functions in section 3 of the manual may have a matching function in section 2, but the functionality is a little different. So in section 3 of the manual, there's a function called exit. Exit will terminate your process. It'll also do additional things to help you, like close open file descriptors, things like that. There's also an underscore exit. Underscore exit lives inside the syscall interface. So when you call that, it's actually doing a software interrupt and actually talking directly to the kernel. So that is going to just kill your process without nice cleanup and things that you might expect. So which one you want to use depends on what abstraction level you're living at. But get PID, get your process ID, is actually a system call.
Can I ask you a quick question?
Sure.
When you run man without a section number, does it go to man 1, or what does it do?
I think it finds the first match.
Correct. Okay.
So like some of these things, if I say man signal, it's going to give me some information about signals in bash scripts or things like that. It's not going to go all the way to section 3 of the manual, which is really where I want it to go. It's going to find it somewhere else.
All right, thanks.
So process, your parent process, every process has a parent, and you're going to see your PPID. You can say get PPID, and that'll return your parent process. This is all a PID-T type, so this is important too. So this is alias to an integer on most systems, but it is its own type. You can't do math with it. You can't do anything like that. So there's reasons why it's separate. And then let's get the process groups and sessions. So this has to do with job control in Linux. So there's a couple of paragraphs that are really important here. So every process is part of a process group. When you run a command or a pipeline of commands in the shell, it's going to create a process group for either that command or a process group for that pipeline. This really has to do with signal handling and job control. So if your process group leader exits, that tends to take out everybody in your process group, and signals are delegated to the process group. So if I send a sig kill or a sig term to my process group leader, he's going to send that to the children. The other thing here is that you have what's called a process group leader. So that's basically the process group ID matches the process ID. That's how you know who your group leader is. And we'll see how this works. A session is around the concept of a controlling terminal. So there's sessions and there's session leaders. When I create and there's a 2-level hierarchy to this. So every process group maps to exactly one session. A session can map to multiple process groups. And a session is how you do things like a control C that will send SIGINT to the processes that are affiliated with that session. So the session is sort of the higher level abstraction, then you have multiple process groups underneath it. And this has to do with job control. You can do a set SID. So this function call right here allows you to create your own session ID. So we'll see processes that have a controlling terminal. When you do a PS, there will be an entry in that PS line that's printed that says PTS/0 if you're connected via a shell, a secure shell, or you'll see TTY in a number if you're connected via an actual physical terminal. So that says who your terminal is relative to the process that's running. When you divorce yourself from your session, you then get a question mark in that field. There is no controlling terminal anymore. There's no way a shell user can log in and affect your system by hitting Control C or BG or FG. He has to actually find your PID and send a signal directly to your PID. So that separates you from that session. And that's the idea of a controlling terminal. And then there's foreground and background jobs we'll go into and some other stuff here. So that's kind of the background on this. So let's look at this code real quick. So I'm using a utility called CMake. So CMake is a really easy way to generate a makefile to build your C or C++ programs. And there's a ton of syntax here. I'm doing the very minimum, very basic. What I do is I set a CMake minimum required. So this says, this just matches what was installed on my system. And this allows me to maintain compatibility going forward. So if I share this program with somebody, if they have at least CMake 3.11.4, I know this is going to work. I then just give the project a name, and then I say add executable. Here I'm going to create something called simple Daemon, and it's based on these two C files. So actually, let's continue walking through. The next thing I have is my main program. It's very simple. I include the standard library, so I can make standard library calls. I include a utility to report my parent group and session. So I send it like a prefix, and it fills that out. And then I return exit success. Exit success is a constant that's defined in standard library. There's also exit failure, and there might be some other ones too, but generally if you use those, instead of remembering if it's a 0 or 1, your programs will be compatible with a lot of things that expect those kind of results to come out. So if you're doing tests in a shell script and you want to see if the program was successful, sticking with exit success, exit failure on the system, that's going to be consistent across those things. Here's the function I wrote to print out some information. So I went to the man pages for these specific functions and included the headers that I needed. So I get my process ID, I get my parent's process ID, I get my process group, I get my session ID. I could have also done a 0 here instead of my PID. It would give me the same result. And then I printf this to standard out. So I just list what this information is and just understand it. And then finally, just a little header file to include that function more easily and other things that need it. So to build this, we'll just say CMake on the current directory. That'll run a lot of tests. It's very similar to the auto tools, if you guys have ever heard of the GNU auto tools, where it'll check if you have the right compiler level and different things and make sure you can build your program. And what it does is it generates a makefile for you. And it's actually a pretty impressive makefile. So there's all kinds of stuff in here. And, all sorts of things it does for you. But we just type make and it'll build it. If I change something, make works as expected. It just rebuilds that one file and then relinks the executable.
So you only have to rerun CMake if you modify the CMake file?
Exactly. Once it's generated, and it generates a lot of stuff here, so if we look at what it's generated for us, you'll see that it has a CMake files directory, a CMake cache, a CMake install CMake. Like, there's all these things that just come out of that, but all you're really writing is this simple list file. And you can have tests in there. You can get quite involved. And I'll show you when we get to the systemd portion of this. I actually add the install. Like if I do a make install right now, it's not going to recognize the target because I didn't tell CMake to do that for me. But you can go that far with this. So we have something called simple Daemon. Before we look at that, let's look at what's running right now. So if we look at this screen, here's my shell that's running. It's bash. It's process ID 6068. And you'll notice that the ps-f command I ran is process ID 6379, but what's its parent? The shell. So the shell follows a standard fork exec type approach. So it's going to fork a new process version of itself and then replace it with the thing you want to run. So it's going to then replace that process with whatever the executable is for PS and run that in its place. But it still maintains the link here between the parent and the child. But what's process 67? So let's go a little further here. Let's grab, let's see, we're going to look at 6068, which is our shell, and 6067. So we're just going to unwind this knot a little bit. So 6067 is an instance of SSHD that's running where I'm authenticated and I have a specific terminal assigned to me. Here's sudo terminal 0. If we go a little further, and its parent is 6052. So if we go a little further,
You looking for KeyLUG? Yeah, let me see, on here.
Oh, look at that, it's on. Wonderful. If I wasn't looking for 40 films, I could find it. No problem.
Hello,
Good morning, everyone.
See? You want to take a couple minutes, let us know who you are, and
Oh, sure. I'm Greg Stevenson, and friend Alex, the redhead. Wait a minute, you lost all that hair. How could you do that? You know, a lot more hair. I haven't seen it in 4 years. Came to donate some old old 486s and all types of PCs, and my wife said, get this out of the shed 20 years ago. Small business owner, defense contractor. I think it works for me. Anybody good with KVM? Kubernetes? Besides you. I'm a Cisco and Juniper person mostly, routing and switch. Seem to always have to get a repo, bring it offline, setting up in the environment, use a CentOS box or something for quick needs, and use some stuff.
so today we're talking about processes and daemons, and just some basics about Linux, and
That is good.
shell job control, and how you create a daemon, and all those good things. So as we continue to wind back, so I have my shell is 6068, its parent was 6067. That maps to an SSH daemon running as me with a specific terminal assigned to it. Notice this does not have a controlling terminal itself, but it's providing the terminal for the bash process. That in turn goes to 6052, which is the privileged SSH daemon that was forked when somebody connected to port 22. So if we keep going back here, up the chain, we'll get to 1691 is the next parent. And that is SSHD. So that's all the options that were sent to SSHD in order to listen on port 22 for incoming connections and then fork a child that's a privileged child that would then go and allocate the terminal and launch your default shell based on your login entries in the password file. So whatever you said you wanted to run in the password file, we handle all that. And then if we go further, you'll notice that 1661 traces to what process? PID 1. So this was started by System D. So we can look at, I'm not going to search for PID 1 because that's just going to come up with everything, but we can actually search for System D. And then if we scroll back here, you'll see that PID 1 is System D running in a switched root and a bunch of other options there. So that's sort of the stack of how these processes are related to each other and how deep we are. You can actually you can display this as a tree. PS minus E, I'm trying to think, it's like H. There's some, or EJH or something. Let's try that.
How's that different from the PS tree command?
So PS tree is probably an alias doing this for you. You know, that would be my guess. But here you'll see this as a tree. I did get that right, wow. So you'll see that 1691, below it is the our Lucente privilege where it was authenticating me, then the SSD, then my bash, then this command I just typed. So that's how these things are all related to each other. All right, so we have this, we have this process we built. Let's go ahead and run it. So this is just gonna run an exit and report some stuff. So I was 6404, my parent was 6068, which is the shell. My process group was the shell, and my session was the shell. So the shell is the controlling terminal. So let's have a little fun with this. Let's, oops, I don't want to edit that. I want to edit, caps lock. So let's edit main C, and we're just going to insert something in here. Sleep, let me say like 2 minutes. All right, is that all I need to do? What am I missing? So let's see what happens, right? Let's make this. So it's going to say, what the hell is the sleep function?
Where was sleep coming from?
So if I say man sleep, to answer your question earlier, it gives me section 1 of the manual, which is more of the shell command, the sleep command. That's really not what I want. So let's do like a man sleep 3. And you'll see that this is a Unix standard type function that I got to include. And then you tell it how many seconds you want to sleep. So we just have to add that header. So we'll go into main C, and we'll just insert here Unix standard H. And then we'll make. All right, so that worked. So now if I run this, it's going to run in the foreground, right? So I can send it the signal control SIGINT, so I can just do a control C. And if I do a PS, it's dead. It's no longer there. But I can also throw it into the background. So let's do that with an ampersand. So it's running, and if I do a PS minus F, it's there, but I'm still the controlling terminal. So can I control C it from here?
No.
So it's not going to propagate the signal because it's a background job. I can type jobs, and I can see means this is job number 1 that's running. Plus means it's the most recent job, and it's simple Daemon. So I can kill it by asking it to come into the foreground and do a control C. And then if I PSF this, it's gone. So the shell has this is where the session leader comes into play. The session, it's controlling this process. I can send signals to this process, throw it into the foreground, the background as much as I want, and do things with it. So eventually we want to divorce ourselves from the shell if you want something that runs continuously beyond the life of any given session here.
If you bring it into the foreground, can you send it back to the background?
Yep.
Yeah, just BG it again.
You can just
Control Z
type BG.
BG again.
Yeah, so let's do that. That's a good question. So let's just do that. So we'll fire up our simple daemon. It's in the background. I'll bring it to the foreground. The signal I want to send it is stop, which is control Z.
Right.
So now it's a stop job, and if I say, hey, what jobs are running, I got a stopped simple daemon, and I can tell it, put it into the background. Now if I
so you
say
have-
jobs.
But you do have to stop it first and then
Yes,
send
you
a
have to
stop
stop.
signal. Okay.
Because it's the foreground process, like any signals I send.
Right, that's why I was wondering, like, you
Yeah.
can't run any more commands there.
So now it's running in the background, and then I can foreground it. Or we can just kill it. Like if we just, PS minus here, we can just do a kill 6491. And then if I hit the return key again, the shell will report that job is dead. So if I look at jobs, there's no jobs running. All right, so let's go to lab 2. So let's talk about fork. So we'll go through the code here real quick. So we have this basic CMake file, same as before. There's really no change. And then I have a couple of different things I include here. So like before, I report who I am. I want to know my parent, my group, my session. And then I call fork. So fork is an interesting function. You call it once, it returns twice. So you get a return as the parent process, and you get a return as the child process. Everything that the parent had, I'm not going to say everything, most things that the parent had are copied to the context of the child process. So if the parent had open file descriptors, the child will have the same open file descriptors. If I do a printf in the parent, printf in the child, they're going to all kind of try to compete with each other right into the console. So they're going to have all of those same things. I wrote a little method here called die. So if fork returns a -1, your host, the only time that could possibly happen is if you've just exhausted the number of processes that can run on your box, or there's insufficient memory, or something really crazy happened. So this will die. If it's greater than 0, it's actually the parent's PID, is what that's set to. So you're the parent, and I'm immediately going to make the child an orphan. I'm going to just drop out. I'm done. I'm exiting. So the child no longer has a parent. If we scroll down here a little bit, you'll notice that I have a report of the initial child, and then I have a report of the reaped child. And I pause for a second. Why am I doing this?
So the system D can clean up.
So system D is going to adopt my process that was orphaned. It's going to reap it, but it doesn't happen instantaneously. So sometimes when we run this program, it'll already be reaped. Sometimes when we run this program, it won't be. And then the second time we report, it is reaped. So we can show that. We'll try this a couple of times. And then I just kind of putter around for 5 seconds, and then child exits. So we can continue to look at the code here. So the other code I want to show you, there's something I'm using in the headers, errno. So anytime a system call or a standard library call fails, there's an error number that's set. And you can use a function called perror, so P-E-R-R-O-R, that just nicely prints what the error was to standard out. I use fprintf and send it to standard error, and I think perror sends it to standard error too. The reason I'm doing this is because I'm going to convert this to a syslog call later, and there's just not a direct mapping between the two. But I print the line number that failed, whatever message I wanted to pass in, what the error number was, and then a string representation of that error number. So string error is actually in the string header file. Errors in the error header file. And then I call exit. So this exit command, or this exit function, actually will do a little more than just kill your process. It will close open file descriptors. If you registered any handlers with an add exit call, it'll execute those in order as well. So you can do significant cleanup if your program dies. And then you'll see that I have my report PGS for what I was doing, and then finally my header file includes all those. So let's go ahead and CMake period. So we'll generate our make files, clean this up and make. So now we have a simple daemon that's going to fork. So let's go ahead and run this. So when I run this, I'm going to actually run this again because I forgot that that's going to do that. So yeah, so a couple of things happen. So the parent was 6664. It forked the child. So here you see the child and the parent are overwriting each other. Let's actually clear this. Make sure they're all gone, and then we'll do this again. So we'll do a clear. Oops. Simple daemon, and then I'll sleep for like 10 seconds so it doesn't mess up the display. All right, so this is a little more organized. So in this case, my process was started as 6673. It's talking to the shell, which we already established is 6068. The parent reports itself after the fork call. It's still the same process, and it exits. The child was reaped. So the child is already adopted by process 1. That's its new group leader and process group, or its new parent and process group. Notice that it's still connected to the shell for the session. So I could still execute job control on this. Like I could do things to this process, send it signals. And then finally, I report that again. If I run this more than once, that doesn't always happen. So here, the initial child was not yet reaped. It's still referring to the parent that either no longer exists or is in the process of exiting. And then the second time it's reported as reaped. So if we get rid of this sleep, or make it shorter, we'll just sleep for a couple of seconds here, because I have a 5-second pause in my program. I can see that the child is running briefly and then it exits. So the child was actually running as 6682 and then it went away. You'll notice that it still has a controlling terminal associated with it, so I didn't dump the terminal on. So let's see, what else do we want to do here? Let me look at the next lab. So if I do this, I'm just going to look at 3. Because I do mess with some of this stuff in the signal handling stuff. I think it's in the signal handling lab already. All right, so let's go to 3. So let's go to syslog. So if we're going to separate ourselves from the terminal, printf is not something you can rely on. fprintf isn't something you can rely on. There may not be a 0, 1, or 2. And actually, before we do that, let's get back to 2 here. We'll do a clear. We'll do a simple daemon, and I'll throw it into the background. And if I do a ps-ef, I can ask what file descriptor. I didn't quite catch it. Let's fix that. Make this last a little longer. 30 seconds. All right, so we'll do a clear. We'll rerun simple daemon. We'll throw it into the background. And now if I do an LSOF on 6117, it tells me what file descriptors are open on this process that was running. So you'll notice that I'm talking to the standard linker, and I have a connection to standard linker and standard C library. My executable, I have that. But I also have 0, 1, and 2. So I have the file descriptors for standard in, standard out, standard error, and they're all talking to that pseudo terminal. So even though this thing's running in the background and it's no longer affiliated with the shell as far as a process group or process group leader, it's still able to send text to this. So I can still printf because I held those file descriptors open. All right, so let's make sure this is all dead now. Good. We'll go to the third lab. So when you're disconnected from the shell, you got to be able to print what's going on. And I'm going to show you how to use syslog. So syslog is unbelievably easy. So here I have the same CMake file. It's just it's 3 lines. It's not very complicated. In my main program, I include syslog.h. And then anytime I want to write something to the syslog, I just say syslog, what level I want to log this at, and then submit what the message is. The interesting thing here is you can do the printf syntax too, so you can have embedded formatting characters, then have additional arguments. It takes a variable list of arguments when you call syslog. There is an open log and a close log method. Those are implicitly called if you don't explicitly call them. So actually you don't have to worry about that. You don't have to open logs and then maybe check if they're open in the child or something like that. You can just say syslog. And if it doesn't have an open log to syslog, it'll open one for you. And then syslog is going to talk to that syslog daemon, so it can send your logging output to lots of different locations. Typically, it's going to send it to the journal, and you're going to see it in the list of journal things that are running. But you could also redirect it to any number of locations, or send it via TCP/IP to somewhere else. So the structure of the program is the same. We're going to fork. Parent's going to exit. We scroll down. Child's going to hang around for a while, see if it gets reaped. And then we have our util-c, where when we die this time, here's where I'm using some formatted characters. I just say syslog, it's an error, print the line number message, error number, and string error number, and exit. And then for my syslog here, I'm printing the same thing. You'll notice I don't need a new line at the end of these lines. So each one of these will be a line in the log. You don't have to terminate it with a new line character. If you did, you'll actually get gaps in your log, which just makes it look kind of weird.
Are log info, log error, those constants defined in syslog.h?
Yep. In fact, if you go to man syslog, I think it's 3. It talks about them. Talks about the open and the close. There's some options you can set. So log end delay is actually set by default. This is don't delay writing it, just write it to the log. You can do some other things here. So you can log the PID when you call syslog. So if you call the open log, you can tell it to do specific things. Some of these are on by default. And then you'll see that there's different facilities you can log to. So by default, I'm logging to log user. But I could messages generated by syslog go to a different facility, or mail, or other things. You can read about facilities. And then here's the levels that are available. So emergency, alert, critical, error, warning, notice, info, and debug. And you can set thresholds on what actually shows up in the log, so you can adjust how much of this information. You don't want all the log debug messages showing up and flooding your var log or your var mount point and then crashing your system. So you can control this, but we're doing very simple things right now. So I can CMake this, and then I can make. So we'll clear and we'll run this. So again, it's going to be similar to before, but before we do this, let me scroll this up. And let's go ahead and follow your log just to see what happens. So here we're going to run the journal control command to trace what's going on in the log. So if I run this, all of those things happen like before. So if I scroll back here, here's my parent. You notice it says the program that was running, the process ID for that program, which matches 6907. The parent exits. It's now reporting 6908, which is the child who was logging. The child was immediately reaped, so there was no delay, but if I run this again, it probably would be. And then the child exits. So if we try this again, so here there was a delay, so parent was 6909, that matches what was logged. Parent exits, child is 6910, still looking to the parent as the process group leader, even though it's not there anymore. And then it gets reaped by system D, and now the child's running. So, and then the child eventually exits after a few seconds. And we could do the same stuff, we could kill it or send it signals. So let's talk about signals. So that syslog is actually very simple and easy to use. So let's go to number 4, and we'll look at some signals. So I'm just going to scroll this down for now. Leave that running. Okay. So again, it's the same CMake. It's very simple, just 3 lines. And now we include signal.h. So you want to register signals with a signal handler. So you want to tell the system, if you receive certain signals, here's the function that deal with it. These are asynchronously processed. They're not in the same thread as your process. So these happen when they happen. So your main process may be doing something else, and the signal handler functions are called separately from that. So you want to be aware of that. You don't want to create race conditions where you're trying to overwrite variables or screw things up really bad. So here I have a child trap, which I'll use for my child process. It'll just print whatever signal it catches. And I have a parent trap, it'll print whatever signal it catches. And then if we go through here, so I report who I am as the parent, I fork, parent reports who it is again, I set a signal trap, and I sleep for 1,000. We're going to ignore this for now. So I'm just going to wait as the parent, just not doing anything. And then eventually I leave. The child will get here as the initial, he'll get reaped. Here we just, after we're the initial child, I don't actually wait to reprint that. I just kind of hang around waiting for a signal to happen. And then I leave. The signal that I'm trapping on is control C or SIGINT. So that's the interrupt signal that the process would send, or the shell would send. And then this is all the same stuff in the util file for reporting who I am and logging errors, and then there's a header file. So let's go ahead and make this. So now we're going to have a little bit of fun. So let's go ahead and run this. I'm going to throw this into the background, and you'll see why in a second. So the parent running is 7083, and the child is 7084. What's going to happen if I kill the child? And this is an important process thing to understand.
The process stops and then because weren't you gonna close out the parent process anyway?
I was, but he's hanging around for like 1,000 seconds, so he's not going to die. So let's see what happens, right? Let's do this. So we're going to kill with an int 7084. That's the child.
Should just kill the child, right?
So the child caught that signal, and the child exited. So let's do a PS minus F here. What does that mean on the second line, where the child process is in square brackets that says defunct?
A zombie process?
It is a zombie process. Wow, this is terrible. We have this process that won't go away. Why don't we try a kill minus 9 to 7084, the child process. That'll kill it, right? Boom. Now if I check, it's still there. Oh, it's a Weasley one. So let's try a kill minus 2. That's interrupt. We'll try a kill minus term. That's like a signal, I think 9 or something. 7084. And let's check that again. It's still
Because a
there.
kill can't touch a zombie process.
Can't kill it.
Yeah.
So what is the downside to a zombie process? It's actually not technically running, so it's not consuming memory, it's not consuming CPU. But what's the bad thing about this?
Just cluttering up your process table is one thing.
It could fill up your process table. It's wasting resources. Not only is it an entry in your process table, there's other data structures in the kernel that it's consuming. So it may have a namespace associated with it, a C group associated with it, like all these other things are still there. Does it have any files associated with it? Are there any mounts? No. So it's not gumming up your file system. So the way you got to get rid of this is the parent has to die. So if I kill the parent, then that will clean up the zombie process. You'll see that they're all gone. Just tell me the parent died. But there's a better way to do this. So if your parent is going to hang around and you fork children.
If you need the parent for other children that it's
like
watching.
a shell, like you're
Yeah.
writing a shell.
Yeah.
So you're forking children, but the parent needs to hang around. What's the right way to do this? So if we go to the main.c, I had some commented out code here. So what you really want to do in this case is, we'll get rid of this. You want to wait on the children to send you their status. In fact, when your parent exits and you're adopted by systemd, systemd will execute the wait command on you. So when it reaps you as a child, it waits for you to exit. It'll consume that. So it'll create a separate version or a fork of itself to just wait on you, so it collects that signal. And if somebody sends it a signal, it'll delegate it to its children. So let's see what happens if we kill the child with this wait signal. Well, what do you guys think is going to happen here?
It would no longer appear in the process table, it won't get defunct anymore.
That's right. In fact, we can actually print this. Let's print the status. Syslog log info child status is. Yes. Alright. So we'll do a make. Implicit oh, what did I forget to do?
Does that include?
Yeah, I didn't include wait.h. There we go. Make. Alright. So we'll run simple daemon again. And I'll throw it into the background, so I'll do a Control Z background. Alright, so now if we kill the child, so I'm going to kill 7150 with an int. Child status is 0, parents exiting. So the parent was waiting on the child exited, the parent exited. If I look at this, they're all gone. So it properly cleaned itself up. The parent doesn't necessarily have to exit after the wait. It could go back into a loop and wait for somebody to type a command and spawn another child or something like that. But the child process doesn't hang around. In fact, we can check that also. Because we properly waited on it, I could put this sleep back in here, but do it after I return the wait. So let's uncomment this and put it right there. So we'll make this again, throw it in, oops, I don't do that. Okay, I got too many things going on here, hold on a second. P-kill simple.
Is the blocking call on the parent?
It is. There's a bunch of flags you can send to it.
Okay.
So generally,
Because it was making me wonder about the scenario where, you know, like a shell or like a web server that has worker processes, you know, anything that spawns off a child and the child is killed or dies for whatever reason, how does the parent continue to work and not have
you would
zombie
either
processes
create another
left around?
thread or something to handle that is how you would do it. So, in fact, Apache, you'll notice Apache spawns a bunch of workers.
Right.
So it's doing a lot of process type activity. So let's try this again. I have too many running. We'll throw it into the background. So we'll check what's running, and we'll kill the child. So let's kill the child. Let's send it the int signal 7181. And just the child exited. So the parent's still running. The child caught the signal and exited, and the parent said the child exited, but there is no defunct process anymore. Even though my parent's up and happy, I don't have a zombie left in the process table. So it's an important thing to do. If you're going to fork and the parent's going to stay around, you got to wait on the children to finish whatever they're doing. Do it in a separate thread or, you know, do it in another process, but you got to wait on it. All right, so that's about signals. The other interesting thing, man7 signal gets into a lot of the information about signals. Signals do have default actions. Some signals cannot be caught. The default actions you're going to find are term, ignore, throw out a core, so not only kill the process, but force it to draw a core, stop or continue. We already saw stop and continue. If you scroll down through here, there's a bunch of things you can use to manage signals, and you know, the thing I'm doing with the signal function, there's actually something that's even more powerful called sig action, where you can set masks and flags and things like that. So, and then here's all the signals and what their default actions are. So signal 1, default action will terminate your process. That's the hang up. So that's when you're controlling terminal leaves or the death of your controlling process. Folks sometimes will code sig hup as a signal they catch as a way to reinitialize their system. So if you have a child running or a daemon running and you change the configuration files, you can send it
Like a
sig hup.
restart if you.
Yeah, it's like a what do they call it? Like a not a cold restart, but like a warm restart, right? Where you're just going to reread the configuration or data files and then do whatever you're doing. So there's a lot of programs out there that'll respond that way to a sig hup, where you send it signal 1 and it just does that. Sigint is normally the control C from the keyboard. The next 3 will cause you to just dump core. These aren't commonly used. Sig kill, if you do just the normal kill command, that's the standard signal that's sent. It sends sig kill. 15 is termination. Some of these can't be trapped. And then it goes down here. Actually, I'll take that back. If you do the normal kill command, it's sig term. It's signal 15. If you send it a sig 9 that cannot be trapped or caught or blocked, that is going to be death of whatever was running. It's just going to kill it.
And that's what kill -9 is, it's sending sig kill.
Sig kill. Kill -9 sends sig kill. Kill -15 is the default for kill, and it sends the terminate signal. Some of these other ones, this has to do with you are not part of that session or session leader, but you're trying to do something with the input. So if you're trying to read from a terminal, but you're not the session leader, you're going to get a SIG terminal input. You're going to get this signal sent to you, and it's going to stop you. It's going to say, what are you doing? You can't do that. So there's information in manual section 7 about signals and signal handling.
And these are all kernel things, right? Like the kernel.
This is all standard library or section 2 of the manual where you're doing system calls. But yeah, you are interacting with the kernel, either standard library, section 3, it's higher level abstractions that are still making these lower level calls, or you can do the lower level calls directly. And you can see, like if we do exit, like the underscore exit, so this is the kernel command to kill the running process. And you'll notice it terminates your process immediately. It does close any open file descriptors, but it's not going to call any registered add exit functions. So it's not going to do any sophisticated cleanup. If I look at the exit command in section 3, I can register functions with add exit and then call on exit to handle cleaning that up. So there are things you can do here, higher level sort of functionality. This in turn does call that underscore exit function. All right, so that's signals. So let's go to section 5. Let's make sure we don't have anything running. Oh, we still have that parent around. Let's kill him. So 7180. Okay. All right. So let's take a look at this. This is the non-systemd way of doing a full daemon. So we've kind of talked about all the pieces and parts. What does it take to actually create a daemon process? Some things in here are kind of controversial. Like, I tried to find the right answer. I started writing daemon processes back on FreeBSD in the late 90s, and you had to fork twice. And there was a reason you forked twice. I don't think forking twice is still required, but I can't find a definitive answer on that. And you get a lot of opinions when you research this stuff. And if you read like a Unix systems programming or Linux systems programming book, they're going to tell you one way or the other, but they don't give you clear reasons why. So we'll talk about what the difference is and why you might want to do this. So again, it's a simple CMake file. And here is my full-blown daemon process. So first thing you're going to notice is I have an integer called running that I set to 1. This is going to keep me up until that gets set to 0. So I'm going to cleanly exit my daemon when I get a signal, and specifically when I'm sent sig term or signal 15, which is the default for kill, I'm going to trap that and say I got that, and I'm going to write 0 to running. So that's going to kill a loop that's running down below. And that's all it does. It's the only function that'll set that or change that variable. In my main function, I report who I am, I fork, the parent immediately exits. The child is now an initial child. I call setsid. I separate myself from bash. I no longer want to be affiliated with its controlling terminal or its session. I want my own. So what will my session be assigned to? It'll be assigned to me, actually. It'll be my process ID. So I'm going to become my own session leader.
You'll change to a question mark
and I'll have a question mark for my controlling terminal. It won't be a controlling terminal anymore. And this gets into why you want to fork twice. We'll get into this. Then I sleep for a second, and then I report if I've been reaped. So, you know, that's a race condition that might have already happened. And then I register for 2 signals. I don't think I need the second signal, but in the documentation, it does talk about the conditions necessary where a sig hub might be sent when the child exits and the grandchild's still running. You might get a hang up. I've never seen that happen because I don't think I meet all the conditions that are required. But you can register that signal, and it's not going to do anything with it. It's just going to eat it. And then sig term, because I check what the signal number is in my handler up top. The only one I'm really responding to is sig term. So sig hub, I register any other signal, it's just going to be logged, but I'm not going to do anything with it. And then I register my sig term handbook. And then I fork again. So in order to get input from a session, you have to be the session leader. Before forking, the child was the session leader. Who's the session leader when I fork again? And I'm the grandchild. gonna be the child, right? Only the session leader can get input from the terminal. So if I'm not the session leader and the session leader doesn't exist, can I ever open a controlling terminal? So this is the reason that some books tell you, or some blogs will tell you, to fork twice. You prevent yourself from ever opening a controlling terminal for your daemon. Although most people don't do that. And I don't know if it's actually necessary. And the third thing is, I've never been able to find a way to open a damn controlling terminal once I'm all daemonized. Like, I can't figure out a way to do it. I've tried like creating PTS, and you know, it might get really low level where you got to create a new device and just do some crazy stuff, but I haven't discovered a way to create a controlling terminal. So I wonder if it's even something you can do once you're doing. So I don't know if the second fork is necessary. It doesn't hurt anything, but you'll see the difference when we do this with System D, that it doesn't do 2 forks, it only does 1. So now I'm a grandchild. I wait to be reaped because my parent, which is the child, exited. I wait a few seconds for SIGHUP that never comes, and then we got to do some other stuff when we're running as a daemon. The next thing we do is we change our working directory to root. Why would we do that?
So you don't write files or something because you don't have permission on the root directory? Or?
So it really has to do with like holding an inode. So if I start a daemon and my working directory is some like removable media or something, you can't ever unmount that because a process has it in use. And it's going to complain, depending on the file system, it's going to complain that that directory is in use. So by setting your directory, your working directory to root, you just avoid all those issues. So if you're going to run as a daemon continuously, don't hold random directories in the system as your default working directory. Like, that just annoys people. And they're like, why can't I unmount this or mount it somewhere else? It's because some rando daemon decided not to do that. The next one is your file creation mask. You should set that. Here I'm setting it to read write for me, read execute for everybody else. So people can look at my stuff, they can't change it. Only I can write any files that I might have open. The next call is a little bit of overkill. I'm asking the system what's the soft limit for open file descriptors on a process and calling close on every single one of them. You don't necessarily have that many file descriptors open. Close is going to just silently fail if you try to close something that's not open. It's not going to complain. It's just not going to do anything. But that's a way to make sure that you're closing all your file descriptors. So what file descriptors do I really want to close as a daemon?
Standard in, standard out.
Standard in, standard out, standard error. Yeah, I don't need those anymore. So you'll see that I do that next. Once I close everything, I'm going to reopen standard error, standard out, and standard in. But I'm going to reopen them to dev null. So I open dev null, read write, and then I duplicate that for the next two. So dupe is an interesting function. This will get file descriptor 0 because I closed everything. This will get 1, and this will get 2. So we'll just do those in order. And then finally, I'm going to do my daemon thing. So I have my working directory as root. I set my file mask. I closed all my file descriptors, redirected everything to dev null. Now I'm ready to run. And basically, I just check that running flag, and if it's still 1, I print tick or tock based on whether I is even or odd, and I sleep for 2 seconds.
So in an earlier example, you did an LSOF, and it showed the standard file descriptors of standard out, standard, those 3. But it also showed you pointed out a linker process or a couple of libraries.
I think
so
it was,
if you did this of closing those, would you also?
So those aren't actually.
They're not file descriptors, or?
They are, but I think they're associated with the executable itself, not with your program.
Okay.
Like I think these are just dependencies that your executable needs to run.
Right.
Not that it's an actual file you're reading from or doing it.
Because that'd be kind of terrifying.
Yeah.
Like,
Yeah.
I'm closing libc.
I mean, let's try and look at it. We'll just do an LSOF once we have this run. And then, what's going to cause this to exit? What's the only thing that's going to cause this to exit?
Sig.
You got to send a signal, right? You got to do a kill or a kill 9 or something. So if I do a kill, or I send it a kill -15 or kill term, I'm going to catch that. I'm going to set running to 0. This is going to clean the exit. Any other signal is going to just kill. Like it's going to be bad. And then I have my stuff where I report who I am and all my information. And then finally we're done. So let's go ahead and we'll CMake this, and then we'll make. So it built it, and we're gonna go ahead and run. Now, I don't actually have to throw this into the background. This thing's going rogue. It's gonna leave the shell behind. It's not gonna listen to it anymore. So let's go ahead and scroll up a little bit here. We can see more of this stuff going on in journal, because that's where really all the interesting things are gonna happen here. All right. So let's scroll back here. So I fire up, I'm process 7432, that's the parent right here. I fork, so the parent just reports its same information, parent leaves. I was immediately reaped by the system D, so system D is now my process group and my parent. I'm 7433 is the child, I still have that session ID. So I call set SID, and then I report my reap status. So now I am my own session leader, I'm my own session, and I'm owned by system D. When I fork again, the reap child exits, and you'll notice that the session ID is for a process that no longer exists. It is impossible at this point, even if you could figure out how to open a control terminal, because you are never going to be 7433, the session leader, unless you like fork again and make yourself call set SID twice or something. So this is why I do that fork twice. It puts you in a state where you can never open a controlling terminal, but I couldn't figure out how to do that anyway, so I don't think it's necessary. And now we're running and we're just ticking and talking, right? So this is going to just keep going and going and going. Let's send a signal to this process. So we'll send a normal kill, right? So we'll say 7434. Boom. It caught it. It's dead. My daemon has exited. If I look for, let's do a peek grab on simple, there's nothing there. So it's gone. There is no daemon running anymore. You had a question about LSOF, so let's go ahead and run this again. We'll wait till we get to the grandchild. Okay, so it's 7451. And if we scroll down here a little bit, there's the thing. So I do maintain those mounts that I need to talk to, like standard library, things like that. You'll see that 0, 1, and 2 are all dev null. I'm not sure where this came from. I'm not sure why that's there or who opened that, but that could be because of syslog, that there was a file script open to syslog. Because I closed everything, so by default, it's going to open up something for me the next time I call syslog. So that could be what that is. And it's using the datagram protocol, so it's talking to syslog via UDP, which is no guarantee of delivery. So if you're sending a crap ton of data to syslog, if you're really verbose, they may not all end up in the log file. Some of those, depending on syslog's ability to handle that, could drop some of those packets and not actually. It's going to do its best, but just be aware. So we're ticking and talking, and again, we can send other signals. We could send to or int to 7451. That killed the program. We'll do a peek grab, but it didn't kill it nicely. It's just dead. So it's no longer there. So that's the way, what I would consider the hard way to write a daemon. So I checked all the boxes. I did all the things you're supposed to do. Fork, maybe fork twice, but set your session ID. Change your working directory to root. Set your file or set your file mask. Set your umask to 22, or sometimes people do it to 0. And have a way to handle signals and cleanly exit. So that's a well-behaved daemon that could run on a system. That's exactly what you're expected to do. So let's go to the last example we have, which is using system D. So this gets a little more involved, but system D is really cool because it does a crap ton more stuff for me. And this, I think, can dovetail to containers. If you guys are going to run containers on an edge device or a smaller form factor system, Kubernetes and OpenShift are way, way, way overkill. You can actually use Podman to run a container, and if you combine Podman with the capabilities of systemd, then you get things like some lifecycle management, self-healing. It'll restart your process if you die. You can tell systemd to do that. Keep me running until I explicitly tell you not. So
Kubernetes, is it running Kubernetes pods, just like individually?
So it's not running Kubernetes pods. Podman is running containers directly as isolated processes. There's a little heavier lift you're responsible for making sure that you're getting all the features and capabilities you want and securing this. Like, you're not gonna get a lot of the nice defaults that come with OpenShift. So it's a lower level abstraction, but if you're on a smaller form factor device, systemd with a Podman container is actually a very powerful abstraction. It gives you a lot of capability. And you'll see how easy it is to write a daemon using systemd. So let's go through this code real quick. My CMake file is a little more involved. Let me do this actually to do it clear. And then, all right. So my CMake, I still have the required minimum version. I tell it my project. I'm going to create one file, one executable based on 2 C files. And then I have some install options. So this is where you get the make install option. I'm going to install some targets. So targets are executables or libraries that you're creating. So I'm saying, hey, take that simple daemon executable and put it in the runtime destination bin. By default, CMake is going to use user local as its standard prefix. You can't override that. You can check if it exists. You can do all kinds of tests here. There's a whole syntax to CMake. But here I'm just saying, put this in user local bin, which is the default runtime destination. Let my brother know, I'll call him back later. The next thing I do is install some files. I need to install the service file or the unit file for systemd. And that goes into etc systemd system. So here I say, here's the file I want to install, and that's the destination to put it. So that's it. When I type make install, it's going to do those 2 things for me. It's going to put the bin there, and it's going to put the configuration file where it needs to go. So let's do that. Let's continue with looking at these files. Okay, now here's the main program. Main is really interesting at this point because it's not doing as much as it used to do. So again, I have my signal handler catching term and exiting cleanly. But look at my main process. I report who I am. I register the sigterm handler. I register that I'm now running. And I'm waiting for the termination to happen. What am I not doing?
Any other crap?
Nothing. I'm not changing my default directory. I'm not changing my file mask. I'm not forking twice or once. I'm not setting a session ID. I don't have to do any of that stuff. All I have to do is just the thing I do. I do the thing I do, and systemd takes care of the rest. Let's look at our systemd unit file. So there's a little bit of content here. So one, I'm a simple daemon service. I have a description. I start after syslog service starts. I want it to know the dependency because I need syslog. You can have a list of things there. Start limit interval seconds. So when you restart, when systemd attempts to restart your process, there's some defaults in place. One is a maximum 10-second time limit and 5 attempts. If you change the 10-second time limit to 0, it means try forever. Don't let me die no matter what. So as long as systemd is running, it'll try to make sure you're running. My service type is simple. This can also be forking. What's the difference between the two? So simple means do all that forking crap for me. Forking means I'm a very traditional daemon. I'll take care of it all myself. So you can tell systemd whether you want it to do these things for you or not. Restart always, restart attempts every second. It's going to run as me. Here's the command I want it to run when it fires this up. So my make install, we'll put this here. Standard input is automatically set to null. That's a default, so I just commented that out, but you can't override that. I also set standard output and standard error to null. My UMask is by default set to 22, but you can override that, so I just include that there just to show you. And then I will run after the multi-user target is working, which means you have a base system up and running with multiple people able to log in, then my daemon will start. And my daemon will start after syslog is available. So that is essentially all you have to write. And there's like 1,000 more options you can include here. Systemd is quite powerful. This is just scratching the surface of what it's going to do for us. But we'll see some of this cool stuff it enables us to do. So I have my util C as before. Notice I don't have a die function. I'm not really doing a lot of system calls that are going to kill me, so I don't have to bother with that. I could. You should have proper error handling, but I just don't need it for this example. So let's go ahead and CMake. Oops, gotta get the current directory. Good. And we'll make. and then we'll do a sudo make install. So it went ahead and installed those files where I told it to do that as root. So a couple of things here. How would I start this program now that it's a simple daemon? What happens if I just do this? Is it going to daemonize? Nope, it's just going to do running in the foreground, talking to syslog, ticking and talking. And if I control C it, it's dead. So it's not there. So what we need to do, it's a system D thing, right? So let's say
System control.
system control. You can start it or enable it. What enabling, and I'll say simple daemon because it's in the official list of where things live. So it's gonna, hey, you gotta be root to do that. Fine. And you gotta be root to do that. Okay. So it creates a soft link. It basically says anytime the system reboots, it's gonna run this daemon. That's what enabling does. If I next do a system control and start, it's gonna run. So let's scroll up here a little bit. Let's just see what this is doing. And I gotta do that. So there it is running. It just reports one time. You'll notice that my process ID and my session ID are the same. Theoretically, I could open a controlling terminal if I could figure out how to do that. There's no way to prevent me, but it doesn't do the fork twice by default, so it's still not doing that. And it's ticking and talking. All right, what's going to happen if we send it a SIGINT to this process?
Well, you told the system to restart or do some research stuff, so it'll start the search, try and start the search.
That's right.
again, I guess.
Boom. I interrupted it. Guess what it did? It's back after a second. Let's do a kill term. This is the one we catch, right? This is the official way to exit our program. Oh wait, I gave it the wrong number there. It's 23 now because it got restarted. Boom. It caught it, it exited. Oh no, it's back. So let's try like a kill
That
9.
zero parameter you put in
Let's
there.
kill that. Let's kill it hard. Can't catch this signal. Boom. Dead. Nope.
But if you had system D kill it, system control stop,
Exactly.
it would stop it.
System control, is it stop?
Yes,
Yeah.
stop,
System control stop,
whatever the thing is.
simple daemon. Boom.
Now it'll exit.
It actually does, oops, I keep forgetting to do that as sudo. It actually catches the sig term, exits, and it's actually stopped. Because system D knows not to restart it again.
So in that scenario, system D is sending sigterm to it, right?
No, yes, system D is sending sig term to it, and system D knows that process is no longer supposed to be running. So it's making sure it doesn't try.
So
to
that
start.
zero parameter doesn't apply because system D told it to stop.
What zero parameter?
I forget what it was.
Oh, no, that zero parameter is important.
Yes, it is, but I mean, isn't it when you said, when system D killed with system control stop, then that wasn't applied anymore because system D took it out.
Correct. Correct.
When
It's not gonna try to
system D,
restart, you're correct.
yeah, when
It
system
won't
D
try to
starts,
restart it.
yes.
It won't try to restart it because system D stopped it.
But
What
if system,
happens if
So this is
it's a
where I
badly
say-
behaving process. So like, will the system D try a sig term first and then give it some time and be like, all right,
System
didn't
D,
listen, I'm gonna
System
kill
D is
you.
not doing health checks here. So System D is simply saying, that was supposed to be running, it's not running, I wait a second and restart it. It fails again, hey, that thing's not running, wait a second, restart it. Like I could have my child keep exiting and System D would just keep restarting it.
like, so you can,
That's why you want the maximum restart time, maximum number of attempts. If you suspect that your thing might go rogue on you. You know, you'll try to restart it for 10 seconds, 5 times, and if that doesn't happen, you give up. So that's how you could do that. So there's a lot of options in System D, but this is where I was saying earlier, if you have a reduced or a small form factor device where you don't want to run a Kubernetes cluster, you don't want to run OpenShift, even single node, you could actually, in your exec start command for System D, have the podman command. Podman, start this container with these options, mount these file points, and then boom, you're running. And then it'll keep restarting your container if your container exits. So you could actually do that. You could have sort of a poor man's Lifecycle management of containers using a systemd podman combination or systemd Docker.
Is Podman a rel thing, or is it a?
Yeah, so we re-implemented the OCI spec. So there's Podman, Scopio, and Builda. The reason for that was that Docker had an actual daemon associated with it that was running privileged. You don't really need that, so if you use Podman, Scopio, and Builda helps you create containers, Scopio helps you move container images around, and Podman is what's gonna run them. If you do that, you don't have to run a separate agent. And you can actually have localized containers. So you can have a container registry or cache local to you.
And the biggest thing is, the biggest advantage to Podman over just using Docker Run or any of those things, or Run C, is ability to run containers is non-root.
Right.
That's why we did it. That's the whole
Yeah,
point.
you can run it, everything is non-root. Every user can have their own sort of cache of their
That drives me
container.
crazy about the default container Docker stuff. It's like all these
I-
processes are running root unless you
I know.
manually
Well,
ship them down.
and
down
they kind of were doing that on purpose. If you think about it, they want you to buy their Docker Enterprise, and then they give you some facilities like that. But yeah, they're not interested in working on that. If you'll figure out security implications.
So all of this is available right here. You guys want to play an experiment at home? So github.com, our Lucente SEJBoss, which I really need to change that. I don't do a lot of JBoss anymore.
There you go.
10 years of KeyLUG. So all the code's under there, and if you guys want to play with this or experiment with it, you can just look at the code and try things out. Man 7 credentials is where you can read about processes. There's a lot of stuff we didn't go over, so one thing to keep in mind, let's close this, kill this. The reason this is called credentials isn't really about the process ID, your parent, or your session. It's about all the crap that's underneath it. Who you are, who your group is, from an identity perspective, what the real user ID and effective user ID is for your process, which determines what it can do. There's a lot more here we didn't get into, but this is really about process identities from a authentication perspective and what it enables you to do. So there's a lot of additional information here and just a whole rabbit hole you can go down into if you want to. That's really all I had for today, so that's about on time.
Nice.
Can you put the GitHub link back up?
Yeah, I can do that. Let's see, it's not in this history, so it's just. Boom. So
That's extremely complete, Rich, by the way. I did look at this actually before we came to this, and whenever I would fork processes, whenever I did this, I took the massive shortcut method of not doing 90% of the proper cleanup, and I suspect most people who are Daemons did too. So this is really good.
And I wanted to try to get, I told Mark, can we do some Linux basic things? Like, so often we're coming in here and talking about different products and things, it's just kind of all over the place, but there's some basic understanding of the system that I think is necessary. The other thing I didn't cover, and this is an important thing too, is a lot of folks will follow the fork exec fork. So where exec is a function you call to change out the executable that's running. So your job management, when you create your daemon, that doesn't necessarily have to be the same program that actually runs as the daemon. You can actually swap that out. So you could have something that reads some of the arguments from the command line, throws them away, and passes the rest of the arguments to the thing that's actually going to do the work. An exec says, substitute this executable in my process space. Make me go away and make me look like this guy. So the bash does that. Bash will fork a new instance of bash, and then it substitutes the PS command for all that stuff, and that's running PS in that same context. So that's another thing that's a possibility that we didn't go over. But that's the bare minimum on how to do daemons and processes and what they are and all the different things that are affiliated with them. So, any other questions?
Thank you.
Yes, it was excellent.